Welcome back, everybody. In this video, we're going to be going over some examples of the mean value theorem. And this is going to be an intermediate leveled video where I explain some very easy examples of the applications of mean value theorem, and in future videos, we'll be applying them to much more complicated functions. So first up, we have f of x is equal to 3x squared minus 4. This is a parabola. And the mean value theorem is right above the screen, so if you do not understand what it is, please do consider reading that over. And if you still do not understand, please do check out my video where I explain the mean value theorem in depth and to its conceptual core. So first of all, we must find the interval of -3, 5, and let's call this interval 1, 2. So we must find a point where x is equal to c such that the slope, the derivative of that point, will be the secant slope that passes through these 2 points. So first of all, f of -3 and f of 5. So that's a pretty bad 5, so I'm going to rewrite that. So what is f of -3? Well, we just simply plug it in to get 3 times 9 minus 4, which is equal to 27 minus 4, which is equal to 23. Now, when x is equal to 5, we get 3 times 25 minus 4. 3 times 25 is 75 minus 4 is 71. And the secant slope that passes through these 2 points is 71 minus 23 over 5 minus -3, which is the same thing as 48 over 8, which is the same thing as 6. So the secant slope that passes through -3, 5 within the function 3x squared minus 4 is 6. And we need to find the derivative between the interval of -3, 5 such that the derivative is equal to 6. So first, find the derivative of f of x. Based on the power rule, we get 6x. And we need to set this derivative to be equal to the secant slope, which is 6. Hence, x is equal to 1. And we see here that x is equal to 1 is between the range of -3, 5, the interval. Hence, our x is equal to c, that c value will be 1. And 1 will be our solution to the first question, applying the mean value theorem. And in the second question, we must always find the secant slope that passes through the interval. So what is f of 1? f of 1 is 4 minus 4 minus 4, which is equal to -4. And when x is equal to 2, that becomes 4 times 8 minus 4 times 2 minus 4, which is the same thing as 4 times parentheses 8 minus 2 minus 1, which is the same thing as 4 times 5, which is the same thing as 20. So the secant slope that passes through these 2 points will be 20 minus -4 divided by 2 minus 1, which is 1, which is equal to 24. So the secant slope that passes through the interval 1, 2 within that function for number 2 will be 24. And let me just check my arithmetic, and I see here that my arithmetic is correct, so we can move on. And now we must find the derivative of f of x for our second question. So f prime of x will be equal to, based on the power rule, 12x squared minus 4. And then we must set this derivative to be equal to the secant slope that passes through the intervals 1, 2. Hence, 12x squared is equal to 28. And x squared is subsequently equal to 7 over 3. Hence, x is equal to plus minus the root of 7 over 3. But we see here that there's an extraneous solution to this question, because the interval is between 1 and 2. But this gives us 2 solutions. One is negative, one is positive. Now, 7 over 3 is roughly 2 point something. The square root of 2 is about 1.414. So we can be sure that when x is equal to positive square root of 7 over 3 will be a solution to number 2. But what about negative, the square root of 7 over 3? Well, since the interval 1, 2 does not include negative numbers, we can be safe to say that negative square root of 7 over 3 will be an extraneous solution. Hence, the solution to number 2 will be the square root of 7 over 3, not plus minus square root of 7 over 3. We must check whether the solution fits the interval, and that is something that you must always do when you apply mean value theorem. So these are some 2 examples of mean value theorem, and in future videos, we'll be going over some more complicated ones, but now I hope that you have a better understanding of the mean value theorem in context.